Okay, this is the pre-lab, a little discussion that's going to introduce you to the concept that you'll be doing in your next in-person lab, and that is intermolecular forces. This is the whole idea behind this is the fact that molecules can stick to each other. And so in this video, we're going to talk about a few things. The first is the fact that when you have a molecule, the electron density, the electrons moving around the outside of the molecule can spend more time in certain places on the molecule, and we'll talk about why that is. And that's related to the property known as electronegativity. And we'll talk about how we can measure the degree to which the electron density is concentrated on one part of a molecule. And then finally, we'll introduce the idea of intermolecular forces, forces between molecules, talk about three different types of them and the relative strength of them. So now a good starting point are the three states of matter. We can have different states of matter at the same temperature, solids, liquids, and gases. At the same temperature, solids have a specific arrangement of the particles. They're held rigidly in place. They don't really slide past each other. In the liquid state, they're still close together, but they can now have some freedom of movement where they slide past each other. And then finally, in the gas, the particles are completely separate from each other. So if all three of these are at the same temperature, it's telling us something about the fact that the particles can stick to each other at different amounts. So what we can draw from this is the fact that particles must stick to each other in some way. Individual molecules must be able to stick to each other. And because we can have different states of matter at the same temperature, that's telling us that the stickiness of these particles can vary. Some particles can stick very well to each other. Some particles are very sticky, and some are not. So that's what we're going to talk about. As to why particles stick together, one reason is if you have an ionic compound like table salt. So there is a magnification of it 100 times of a crystal of table salt. So you can see it's got this nice geometric shape to it. The reason why the individual particles stick together in table salt is because the particles have opposite charges. So in the case of that, it would be sodium and chloride having a positive and a negative charge. And as we know, opposite charges attract each other. And so that's what causes these particles to stick together. When we get to water, though, something peculiar is that the water molecule itself is neutral, doesn't have a charge overall. And yet we know that we have ice. So the question is, what's causing it to stick? Well, one clue is in this little video I'm going to show you. Here's a video of a stream of water. The water's just been colored so you can see it. And what happens in this video is there's a rod that's been charged by rubbing it with some fur. And when the rod comes near the water, you can see that it's pulling it. The charged rod is actually pulling the water towards it. So the idea that's at play here is that we have charges. So there's got to be something about the water molecule being charged that's causing that to happen. And yet we know that it's neutral. So those two things are kind of contradicting each other. So why can one water molecule attract another one? And that's going to be the big idea that we're going to talk about in this video. So to start off, water is kind of a complicated molecule. So let's look at one that's even more simple, hydrogen fluoride. So I'm going to bring up a molecule simulator here. So hydrogen fluoride is right here. And what I can have this simulator do is show us the spreading out of the electrons, the electron density. So it's color-coded in very simple black and white and gray. The place where the color is darker is around the fluorine, and you'll notice that has a higher electron density. On the other end, we have a whiter color, and that's a lower electron density. So in this molecule, the electrons are not going around nice and evenly. They're actually spending more of their time around the fluorine atom. So there's the picture of the electron density of the fluorine atom, a fluorine molecule rather. So the fluorine molecule has two ends. It has this end of high electron density and an area of low electron density. And so we have a specific term for that you're probably familiar with. Just like the ends of the Earth are known as the poles, a molecule that has two ends to it, two different ends, is known as a polar molecule. There are some molecules for which the electron density is not concentrated on any one place. It's spread out nice and evenly, as in the case with this hydrogen molecule. The 1 and the 2 just refer to the numbering of them. So we can see that in here, the electron density is nice and evenly spread. In this case, it's called a nonpolar molecule. Now, if you have the same idea but apply it to bears, then what you've got is a polar bear. You done laughing now? Okay. So why is that? Why is it that fluorine is able to pull this electron density towards itself in the molecule? Well, that has to do with a property called electronegativity. It's basically a measure of how good a molecule is at pulling electrons towards itself when it's sharing electrons with another more atoms. So what causes this? What causes electronegativity to come about is the fact that the atom has protons that are positive in the nucleus and they attract electrons which are negative, orbiting around the outside. So this attraction can vary in strength. The attraction can be stronger or it can be weaker. And there's different components of the structure of the atom that are going to influence how strong that attractive force is. And then that's going to govern how good the atom is at pulling electrons towards itself when it's in a covalent bond. One factor is the number of protons that are in the nucleus. The more protons you have, the more of a positive charge that you have. So this is known as the nuclear charge, the charge on the nucleus. So if you have 4 protons in the nucleus versus just 1, that's going to be able to attract those electrons with more strength than just 1 proton. In the periodic table, this shows a trend. So as you go from left to right, the electronegativity tends to increase with the exclusion of the noble gases, as they don't really form bonds very easily. And in order to have an electronegativity, you got to form a bond. So I'm going to look at this particular period on the periodic table, this row, starting with lithium and ending with fluorine. So there we have them all lined up. Just less the light just went off. Sorry about that. We have lithium at the left, and then all the way over on the right, we have neon. So the atomic numbers are shown below. So we have 3 protons all the way up to 10. So there's 3 protons all the way up to 10. And so because there's more protons, that is why the element can attract the electron more strongly. Now, in terms of the electrons, these are all in the same energy level. This valence electron is all in the same energy level. So you can think of it as having the same distance away from the nucleus. The other factor that affects how strong the attraction is to the electron are the number of core electrons. Core electrons are essentially electrons that are not valence electrons. And basically, the more core electrons that you've got, the weaker of an attractive force it's got. So here are 2 atoms where one of them has 3 core electrons, and then we have the valence electron. This one doesn't have any core electrons. It just has this one valence electron. So because there's no electrons in the middle getting in the way, it's able to have a stronger attractive force. So the one on the bottom would have a stronger attraction than the one on the top. This property where the core electrons kind of block the attraction, we call that the shielding effect. A shield blocks something. Okay, on the periodic table, I'm going to look at this first group with lithium and sodium and potassium and rubidium and cesium. So there's this column on the periodic table. They all have 1 valence electron. But what's different is as you go down, the number of core electrons that they've got, and you can see that they increase pretty dramatically. So as you go down, there's going to be more shielding, and as a result, there's going to be less of an attraction to the valence electron, and that's going to result in a lower electronegativity. So as we go down the column, in general, you can see that the electronegativity tends to decrease as you go down. So what all of this comes down to is this trend on the periodic table where the further up a column that you go and the further to the right, those elements are going to be good at pulling electron density towards themselves in a covalent bond. Up at the top right, we have fluorine. Fluorine is going to have the highest electronegativity of all of the elements. Okay, now the electronegativity is going to govern what kind of a bond that we make, being either an ionic or a covalent bond. So let me bring up another simulator. Okay. Okay. So here's a molecule that's just made of 2 atoms. And then I have the electron density here. And right now you can see that it's pretty even right now. This little diagram here is going to show us what kind of a bond that we have going on, whether it be covalent, which is the sharing of valence electrons, or ionic, which is when electrons get fully transferred from one atom to another. Down here, we can slide and change the electronegativity. So right now we have 2 atoms that have similar electronegativity. What I'm going to do is make the atom B be more electronegative. And then what you want to do is pay attention to this area right here, the bond character. So as the difference in the electronegativity goes up, you can see that that electron density is starting to favor the atom B. And then also the bond character becomes more ionic. If we take this and make this more electronegative as well, then you can see that it starts to drift back in the other direction. So what this comes down to is that if there's a difference in electronegativity, then that's going to affect the bond character. If they have a similar electronegativity, then neither one of them are going to pull the electrons towards themselves. It's as the electronegativity of one of the atoms increases, that's when you're going to start to see this electron cloud getting distorted. So when we have that, when we have a separation of this electron density here, we have a way of representing that with an arrow. This arrow is known as a bond dipole, and it's just another word for polar. Dipole means 2 ends. And this arrow is going to point in the direction of the higher electron density. This is going to stay constant no matter how the molecule turns. If it turns around, it's still going to be pointing towards B. It's going to point towards the more electronegative element. So the way to think about the different types of bonds, ionic and covalent, is it's not really a binary. You're not really in between. You're not either in covalent or ionic. It's really more of a continuum, kind of like how a rainbow, the colors in a rainbow kind of bleed into each other. And so what we've got is we can kind of subdivide this into different types of bonds. On the left-hand side, where the electrons are being shared nice and evenly, we call that a nonpolar covalent bond. Nonpolar just means it doesn't have those ends on it. And then if you have 2 atoms that have the difference in electronegativity, then you have what's called a polar covalent bond. That means that they're sharing the electrons, but one of them is hogging the valence electrons. And then if that kind of increases, if it gets more and more electronegative, then eventually it gets to the point where the electrons fully get transferred from one atom to another, and you have what's called an ionic bond. Today, we're going to be talking just about the covalent types, the nonpolar and the polar covalent bonds. So we have a way of quantifying how polar a molecule or a bond is. So I'm going to bring that simulator back up again. Okay, so you can see that as if I have a nonpolar bond, you can see that there really isn't an arrow there, and that makes sense because the electrons aren't getting distorted in any direction. But as I start to increase the electronegativity, you can see that that arrow, that bond dipole arrow, starts to get bigger and bigger and bigger. So that's when you have a single bond. Now, molecules can have more than one bond. So let's say we have a molecule that's made of 3 different atoms. And if I make it so that the middle one is the most electronegative, and I will show and there's the individual bonds right there. So the middle one, this atom right here, has the higher electronegativity of the two. You can see that each bond has that dipole arrow pointing towards it. So now, because these arrows are what's called vectors, which means that you can add them up or cancel them out depending on which direction that they're facing. Both of these arrows are pointing upwards. This one's going up and to the right, and the other one's going up and to the left. So if we were to combine those, what we would get is an arrow that's going upward. So this arrow, this yellow arrow, is known as the molecular dipole. Molecules themselves can be polar or nonpolar. So it depends on who is in the molecule, which elements are there, and it also depends on the geometry. For example, this molecule is bent, and so that's going to cause these arrows to point in a certain direction, and because they don't cancel out, then they actually kind of add up and they point upward. If I change the shape of the molecule, so what I'm going to do is I'm going to turn it into a linear molecule. Keep an eye on what happens to the yellow arrow, the yellow dipole arrow. It gets smaller and smaller and smaller. So what this is like, think of this sort of like a tug of war where both sides are pulling equally as hard. In that case, the forces cancel out. And in this case, the dipoles cancel out because they're pointing in opposite directions with an equal amount of force. So it cancels. And so molecules can have polar bonds in them, but the molecule as a whole does not have a dipole. And so that molecule would be considered nonpolar. So that's a little bit about the geometry of it. So we have a way to quantify how polar a molecule is. So we have something here that's called a dipole moment. And all that means is it's a property that has a direction and it also has a number associated with it. The direction we've already talked about, that was that dipole arrow that we were looking at, the arrow that points towards the more electronegative element. The number, which we're not really going to discuss very much, is a number that's measured in a unit called Debye, where the bigger the number is, the more polar that the molecule or the bond is. So for the hydrogen fluoride molecule, you can see that the molecular dipole is pointing towards the fluorine because that's where its electrons are getting distorted. So hydrogen fluoride is a polar molecule. The measured value of the dipole moment is 1.03 Debye. Again, the bigger the number it gets, the more polar that the molecule is. So we can compare this to another molecule. Here is a molecule of water. And what you can see in here is that it's a bent molecule, and hydrogen and oxygen have a difference in electronegativity. So because hydrogen has a lower electronegativity than oxygen, oxygen is going to be pulling the electron density towards itself. So overall, what we've got is, what we have is a molecule where the electron density is higher around the oxygen and lower around the hydrogens. And you can see that there is a molecular dipole, this yellow arrow, and it's pointing towards the oxygen because that's where the electron density is getting focused. So the value of water in terms of the dipole moment is 1.85 Debye. What this allows us to do is to make comparisons between two molecules. Hydrogen fluoride has a dipole moment value of 1.03, and then water is 1.85. So what that is telling us is that water is more polar. It does a better job at pulling those electrons into one location than is hydrogen fluoride, which we would call less polar. All right, now what this causes is if you have two polar molecules, what they've got is when you have a polar molecule, it has a positive end and a negatively charged end. Only it's not a full positive and a full negative end. So we use the Greek letter delta in its lowercase form. They're probably used to delta being the triangle. That's the uppercase version of it. This is the lowercase version of delta. And all it really means is kind of. This means that this molecule, this end of it, the fluoride end of it, is kind of negative, and this end is kind of positive. Well, what we looked at earlier with the water stream is that we know that opposite charges attract. So if one hydrogen fluoride molecule comes near another one, and they're oriented so that the opposite ends are close and the the same size ends are facing further away from each other, then there's going to be an attraction that happens right there. So this attraction that happens between molecules because of the opposite charged sides is called an intermolecular force. It's what causes molecules to stick together. It's the reason why we have solids and liquids. There are different kinds of intermolecular forces, and this one, which arises between two polar molecules, is known as a dipole force. Again, dipole, if you think about what that word means, dipole means two ends. It's just another word for polar. So a dipole force, another way to say it, is a polar force. Now, there is a special instance of a dipole force that results in it getting its own name. This is a type of a dipole force that happens in water. So this type of force is very prevalent to us. And also it happens to be especially strong. And the reason is because in the water molecule, oxygen does a very good job of pulling the electron density towards itself. And hydrogen, what's left here, is basically a bare proton there. So this allows water molecules to attract each other rather strongly. And so you can see that this type of intermolecular force, which is a kind of a dipole force, is given its own name. And so we call it hydrogen bonding. It's when you have hydrogen in a molecule directly bonded to, so meaning it's got to be directly attached to one of these three elements here: nitrogen, oxygen, and fluorine. You may see that chlorine is also included in the list, but that sort of depends on which reference that you're using. Okay, so the name of this, again, is hydrogen bond. It involves hydrogen, and hydrogen has to be directly bonded to either oxygen or nitrogen or fluorine. All right, now, the third intermolecular force that we're going to talk about happens between non-polar molecules. So hydrogen at room temperature is a gas. However, if you cool it enough, if you get it cold enough, and you have to get it pretty cold, it does turn into a liquid. Now, what that's telling us is that the particles, the hydrogen molecules, are able to attract each other, although in weak amount, it's still there. There's still the ability of nonpolar molecules to attract other nonpolar molecules. And so that's the third type of intermolecular force that we're going to talk about. So if two hydrogen molecules come near each other, there's no oppositely charged ends. So you'd expect that they wouldn't attract each other. However, those electrons are not static. They are moving around. So it's possible that at any given point in time, that the electrons may have a higher density around one of the hydrogens or another. So this would be a snapshot in time. We have a molecule that is temporarily polar. And if it comes near another one, then it's going to be able to attract it. So if you have this molecule that's polar for just an instant, and it comes near another hydrogen molecule, the negatively charged end is going to push away those electrons on the left-hand side. And so what we've got now are two molecules that are polar just for an instant in time, but enough so that we have this type of a intermolecular force. This force is known as a dispersion force, or it's also called a London dispersion force. And that is our third type of intermolecular force. Now, this type of force is not permanent, it's fleeting. But when we're working with the number of molecules that we're usually working with, it adds up. And it goes back to normal. So right now, we have more or less a ranking of the relative strength of these intermolecular forces. Dispersion forces tend to be the weakest, followed by dipole forces, and then hydrogen bonding tends to be the strongest. So that's the order in which they go. Now, there's a big asterisk associated with this. See how big that is? That's a really big asterisk. This is true when you have molecules that are of a similar size. The way we quantify the size of a molecule is by the molar mass, the formula mass of the molecule. That's one way to quantify how big the molecule is. And that's something that you will be exploring in the in-person lab when you get to it. Now, why are intermolecular forces important? So as we talked about, there's molecules, what they're made of, the elements that they're made of, as well as their structure. The three-dimensional structure will determine whether or not they're polar, and the polarity determines how strong those IMFs are, the intermolecular forces. And what that governs, what intermolecular forces govern, as I've mentioned a couple of times, is the state of matter that something's in at a certain temperature. So if you look around you at room temperature, there are gases around, there are solids, and there are liquids. And that's related, that's a direct result of the strength of their intermolecular forces. IMFs also govern the temperature at which changes to different states of matter occur. So the temperature where something boils or something melts. And these are ideas that you're going to explore in the pre-lab this week. You're going to look at how boiling a point is affected by the strength of the intermolecular forces.